Okay, let's see. So, yeah, before I forget, so I do hope to have your exams graded by the end of the week. I was just working on writing the last few problems for the final, so I already have them all written. I'll post them tomorrow. Basically, as I was saying before, there are only two more classes left because next Monday I'll just do the same thing I have been doing before all along, where like I just turn it into some sort of like office hours. Um, so the only two topics left are oh, actually I should, let's see if I can airdrop this to my computer first. The only two topics left are another form of relaxation, which is called Lagrangean relaxation, is what I was going to tell you about today. And the and then there's like a cool uh, topic as well, which is called disjunctive programming, which is how do you maximize functions uh, where the where the region is not convex, but a union of convex sets. This is actually like an interesting topic worth checking out. So I'll talk about that one um on Wednesday. But yeah, only like so whatever I cover in these two classes, that would be the last topic, and the last two topics for the course. But I'll post all the examples, all the problems tomorrow. I also wrote already the solutions, so I'll post them with the solutions so that you can look at them as well and practice.
Where to be homework before
I won't make it a homework, but yeah, it would be.
practice problem.
But there will be like these practice problems, yeah, that you can check. So there are not that many new topics after the third exam. So like it's like this integer programming. I guess you should also know how to do the network thing with the bipartite graph, like how to set it up. And then this Lagrangian relaxation, there is an application to network flow, which I think I should have enough time to discuss it today. And then this disjunctive programming. But yeah, I put problems for each of those on the new PDF, and once I have posted them tomorrow, I'll send an announcement. I'll also include the time and room for the final because I just forgot to send that as well. Uh, but yeah, I don't want you to work on it. I mean, like the assignments, like you can just look at those problems, but in case some of you have to focus on other things before the finals, like you can just do that instead. Then is this connected? Oh, it's not connected because I forgot to connect it here. This is adjunctive programming. Oh, I think I need to connect this again. Let's see. Ah, finally. Okay, so today we're going to talk about, as I was saying, this topic called Lagrangian relaxation. So as I was saying before, relaxation is just a word that you give to all these optimization problems where you make it easier somehow. So whenever you make the optimization problem easier, then you're relaxing it. So again, this is like making the problem easier in some way. So before, the relaxation that we had studied was like if you had like this max problem where the solutions had to be integers, right? Like all the coordinates had to be integers. The relaxation was, oh, let's just forget about that. So solve it pretending that there's no constraint on the variables being integers. You solve it as a regular problem, and then you do the branch and bound thing where you just branch depending on whether like the variable, like what are the coordinates that doesn't have like an integer variable. This is like a different type of problem. So in this setup, okay, you're trying to find the max of a function. The usual thing, that hasn't changed throughout the entire course. Like all the variables are non-negative, right? Um, you have like this inequality constraint, and you are asking the variables to be integers, okay? The variables coordinates of x are integers. So it's still like what you would call like an integer program as before, because we still are trying to find integer solutions, okay, to the problem. So the previous relaxation that we had discussed, like the initial one was like, oh, let's just pretend that this one does not exist, right? And you just solve it as a traditional linear optimization problem. In the Lagrangian relaxation, it's a different perspective because I'm going to keep this condition, but I'm kind of, in a sense, going to forget about some of the constraints, but in a clever way. So when you do Lagrangian relaxation, what you do is you split the problem. uh, what you do is like you separate the constraints into two classes. So you separate the inequality constraints into two types, the easy inequalities and the hard ones. So like the hard inequalities, or let's call them difficult. The difficult inequalities. I'll do an example in a moment just to show you how this looks. Inequalities, which I'll just write as A1x less or equal to B1. And then the easy inequalities, okay? Which I'll just like not write as A2 times x less or equal to B2. Okay, so for example, let me write down something to have like a concrete idea. Okay, so let's say you wanted to find the max. So let's say you wanted to find the max of 2x1 plus x2, subject to the usual constraints that each variable has to be non-negative. Okay. And then I will put the following three inequalities. So for x1 plus 5x2 less or equal to 20, x1 less or equal to 3, x2 less or equal to 3. And then I will put that x1 and x2 should also be integers. So must be integers. Which if you want to draw that on the plane, the way this region looks like, let's see, I'll try to draw it. you have this line which is at 5, 0, 0, 4, and then you have x1 and x2 equal to 3. Um, okay. And that's roughly how the region looks like. Okay. So that would be the problem in this situation. Okay, so what I'm saying is that when you're doing Lagrangian relaxation, you kind of choose of the inequalities, which ones you want to consider hard and which ones you want to consider easy. Okay, so in this case, we have three inequalities to choose from, right? I mean, of course, this is like a simple example, but the one that I will consider a hard inequality is the first one, just because that involves x1 and x2. So of the three, the last two are just like for one of the variables at a time. So I'll choose as my hard inequality the first inequality, and I'll declare the other two to be easy. Or like I think I was calling this like the difficult inequality. So this will be the difficult one, and these two will be the easy ones. Of course, for the method, like that is like up to the person, right? Like, so the method, like, you just tell it which one is hard, which one is easy. Like, in practice, you do try to kind of, I mean, that of course would take some experience, but in practice, you do try to, just keep the inequalities that like you want to, I mean, what we'll do is kind of remove the hard inequalities in a way. So you want to kind of like remove the inequalities that make the region kind of like more complicated. Okay. So, okay. So once you have made your choice of what is hard and what is easy, in the Lagrangian relaxation, what you do is literally remove the inequality that you call, or inequalities. You could have removed more than one. You remove the one that's considered, like in this case, I only considering one difficult, so you remove the difficult inequality. Okay, so what do you do in Lagrangian relaxation? So you remove the hard inequality, which should have called them like from the constraint set. So 2x1 plus x2. Well, there's something that needs to happen here. That's why I haven't like closed the parenthesis for the function. But let me just write the easy inequalities first. Oh, by the way, like I guess like the region, like like is the lattice point. So it's not, because I still want the everything to be like integers. But I'm just saying, like if you forgot about the integer condition, that's how, you know, if you if you draw everything without worrying about whether it's integer or not, that it would look like the pink region that I colored. But if you just look for the integer points, like it would look something closer to that. Of course, there you would need to be a little bit more precise about how you do it, but you'll see it's not that important for us in the moment. Um, okay, so the idea is that if you kind of, again, I still want to make these two to be integers. But in this case, what happens if you look at it, like the region itself, like because now it only has these two constraints, right? Like instead of like working with this shape, which is like some sort of polyhedron, now you're working with the square. And again, like if you were looking for the integer points, they would be these ones. No, I guess. Okay, so far so good. Everyone with me? So like the region did become simpler, right? You change from that polyhedron to that square. Of course, there must be like a trade-off because you cannot just like if you just start removing inequalities at like at free will, then like you are changing the problem like drastically, right? So the idea of like the lagrangean method is that you introduce a penalty that kind of wants to enforce that inequality. But the idea is that you do that through like inserting the inequality into the function itself. So what you do here, I'll kind of like mention this like explicitly, but you incorporate the inequality into the function. You incorporate the inequality that was removed into the function. Let me use the color of the inequality that I removed. So you incorporate inequality removed into the function. So the way you incorporate it, you'll see why I do it this way, is I'll add like a term which involves a constant called lambda, and that's where like where Lagrange comes from, because this is related to the Lagrange multiplier method, if someone has seen it before. But then here lambda will be a positive parameter. Here lambda is greater or equal to 0. It's a constant. So the idea is like the inequality that was removed is reabsorbed into the function that you're trying to optimize. Kind of like that's the point. Yeah.
Does it like, does it matter if it was like less than or equal to, or like greater than or equal to?
Oh, if it's greater than or equal to, then you do have to do the trick first, like
It has to be like.
correct, yeah. Yeah, at least for the one that you're trying to reabsorb into the function. Yeah. If you flip the inequality, then like it will flip the sign somewhere there.
You like put 4x1 plus 5x2, you put it to the right, because it's gonna be greater than or equal to 0.
Correct. Yes, yeah. So right, like the reason why I flipped these two signs is because right, if you put it like at 0, then it would be 20 minus 4x1 minus 5x2, and that's how I'm thinking about the inequality in this case. But it was important, kind of like that it was 0 less or equal to something. Okay. Now, okay. So let me explain what the strategy here is. So this expression, right? Like what is the name that let me call that L sub lambda. So let's call, and I'll explain why you do it this way. So call L sub lambda, the new function, okay? Oh, let's put like the dependence on lambda here. And I guess I suppose it depends on x1 and x2 as well. Okay, so why is it being set up in this way? The reason why the function is constructed this way is that the function penalizes you if you violate the inequality. That's how like has like an economic interpretation if someone is interested in that. But like I'll show you what I mean by this. So the construction of this function is designed. It is designed so that it penalizes you for violating the inequality that you dropped. Okay, for violating the inequality you removed. So why is that? How can you see that that's happening here? Because the original inequality, right? Like the original inequality, was that 4x1 plus 5x2 was less or equal to 20, right? So this is the original, the inequality that was removed. Um, so what happens if you violate this inequality? That means that the less or equal to turns into a greater than, right? Like that is like that's the opposite of the inequality. So the violation of this inequality translates to 4x1 plus 5x2 is greater than 20, right? Like that would be the inequality being violated. Is that making sense? So far, so good. Is that reasonable? And then if this is less greater than 20, what's the effect on the function, right? If you look at the function, if you look at the function, whenever the inequality is violated, that means that this term next to the lambda, right? Like the term that lambda is multiplying becomes negative, right? So this would be negative because you're violating the inequality. If this constant lambda, which is you can call like a multiplier, that's kind of what the Lagrange multiplier method does in a sense. If this constant, we're always taking it to be positive. Positive times negative is negative, right? So this all becomes negative because the multiplier, the constant lambda is positive. And so the violation of that inequality drops the value of the function, right? Because whenever the inequality is violated, this makes is a negative term, right? But that's bad because we want a max. So we would like this to be as large as possible. So we would actually like this contribution to add, like not to drop the value of the function. So this is bad because we were after a max, right? So, kind of like the logic behind it is that when you're satisfying the inequality, that actually helps the function, right? Because it kind of like adds an extra term that would increase its value. So this like drops. So this term drops the value for the function of the function, which is not good. So it's not desirable because we are looking for a max. Oh, what happened here? Sorry about that. Give me a second. Just is that making sense? Kind of like the philosophy behind it. So the idea is like you kind of reincorporate the inequality into the function to make the region you're working with easier, and the trade-off is to work with a more complicated function, but that kind of carries a penalty for violating the original inequality. So that's kind of like the gist of it. In fact, the way this is all designed, if you believe this, it's not too hard to convince yourself. Like, let me write it like this: that the max of the original problem, right? So, if in fact, it's not too hard to see. It's not too hard to see. That the max of the original problem. Let me copy paste. You know, oops. The way this is also built is so that this max. Uh, the max of the original problem, if you take all the inequalities into account, is always less or equal than the max of the modified problem because of what I just said. So for any value of lambda, regardless of the value for lambda regardless of which lambda you use, as long as it's not negative. That for any lambda. Why? Because again, the idea is that if you have a point in the original region, this inequality is always satisfied. Since this inequality is always satisfied, that always would add a non-negative amount to the new function, so that it would bump it up. That's why like kind of like this max is smaller or equal to that max. Is that making sense? Um, and that is actually sometimes it is called like a Lagrangean dual because of this reason. Because if you remember the weak duality said that the dual problem always had like a value of the function at least as high as the original one. And this is kind of like similar to this. So it gives you like an upper bound on the max. Okay, so it's kind of like similar to like a weak duality principle. So this is similar. So let's call this max like let's call like usually I think like let's call Z star the original max, and let's call C star lambda the new max, right? So this is the new max depending on lambda. So what I'm writing here is that the original max, the max of the original problem you were trying to solve, is always less or equal to the new max in terms of lambda. So it's kind of like a version of duality, because again, the dual is, of course, it's a different flavor because like in the dual, you change literally the variables. We're not changing the variables, but it's similar in the sense that it gives you like an upper bound on the max, which is what the weak duality had said. So it's kind of like, so this new problem bounds the max from above. That's kind of one way to think about it.
Does the lambda need to be larger or equal to zero?
Well, right, because otherwise, then if it's negative, then it messes up like the right.
So, we should add it to the constraint one.
I mean, I did the things like here when I write it like I did write here lambda greater or equal to 0, but when I write it like here, right, like implicitly you would assume that. True. Yeah. So it's just that I'm not putting it as a constraint per se because I'm still thinking about this as a parameter. right? So like the variables of this problem are still x1 and x2, right? It's just like lambda is an extra parameter. It's kind of like psychologically a bit different, you know? But yeah, like always think that lambda is not negative. Yes, for sure. So this new problem gives a bound for the original problem. Is that making sense? And then kind of this is true regardless of the value of lambda, right? So then and I'll show you how all of this works in this example. But the idea is that since this is true regardless of the value of lambda, what you would like to find is like minimize this over lambda because the minimum of the maxes would be the best bound that you could get from this method. So after so kind of like the idea is kind of like you solve the problem for lambda and then you take the minimums of these lambdas, like, you know, just to find the best possible bound. Because again, the best possible bound would be like the closest one to the actual max that you care about. Uh, you don't want the bound that's too far away from the actual max that you care about. You want like in duality is exactly the same. That's what duality is great for. This is not necessarily going to be the same. There might be a gap, but you want this gap to be as narrow as possible. Okay. So that after you solve it for lambda, what we are going to try to find is the minimum over lambda of this function. So let me write that down on then I'll show you how all of this looks like in a moment. So after solving for lambda, you find the mean over all possible lambdas of this value, because this will be the closest bound to the max things. But and this is actually this other you know, and so again, you're making the problem easier. It's called like a relaxation in the sense that you have simplified the inequalities that you're working with. So that's why it's used, the word relaxation is used, because like you made your life easier. But this is also like a useful relaxation in practice. So that's kind of why I I wrote it here. Like if I have time, I'll mention how it's used for these network problems, but at least I do want to kind of like do this example in full detail so that you have it there. But okay, questions about this so far so good. Um, okay. So let's try to do it for this problem. So in our example, the relaxation look like the relaxation looks like that's what it would look like. So let's focus on this and I'll show you that this is really easy to analyze, just these two inequalities on the function. You don't even need the picture. It's very algebraic. That's kind of like the reason why we're doing it this way. So um, So there's another way to write this. This is a max of 20 lambda plus, let's factor out the, let's see, 2x1, 1 minus 2 lambda plus x2, 1 minus 5 lambda. Okay, so what I did here is that kind of like I factor out the common terms. So there's what has an x1, this term has an x1, this term has an x1. So I factored that out here. So I get 2, well, I mean, I took out the 2 as well. So you get 2 and then 1 and then minus 2 lambda, which is here. And then similar with x2, where's an x2? There's an x2 here and here. So I took that one out. So you get 1 and then 5 lambda. Does that make sense? And then the idea is that you're thinking of lambda as being fixed in this problem, right? Like lambda is like a fixed quantity, positive. So this first term doesn't really depend on the value of x1 and x2, right? So it's kind of like a constant because the max is over x1, x1, x2, if that makes sense. Like just to specify, like you're trying to find the max in terms of x1 and x2, right? So the 20 lambda is kind of like a fixed amount. Like think about it, if lambda were like a half, it would be 10. So the max is just 20 lambda plus whatever the max happens to be. So this max is the same as 20 lambda plus the max over x1, x2 of 2x1, 1 minus 2 lambda plus x2, 1 minus 5 lambda. So you just have to focus on you know, on this part of the function to maximize it. That's what I'm trying to say. That makes sense. And now we just make cases because the question is like, the idea is that depending on how big lambda is, this factor could be positive or negative, right? So for example, if both were positive, let me put it here, you know, if these two factors were positive, right? If these two factors are positive, remember our variables are always positive to begin with, like x1 and x2. So if these two are positive, what you will to make this as large as possible, what you would just choose is x1 and x2 to be the largest they could be, right? But if, for example, this one is negative, if this one is negative, then you want this to be the least contribution that it can contribute. So you would choose x2 to be 0, you know, because that's the least x2 can contribute. So you just make cases depending on where lambda could land. So for example, and the cases are kind of like easy to analyze. So if I want like, if say I want 1 minus 2 lambda to be positive and 1 minus 5 lambda to be positive, right? Well, that means that lambda should be less than 1/2 and lambda should be less than 1/5, right? Well, of course, like the winner is like the smaller one. So what that means is that if lambda is between 0 and 1/5, right? Again, if lambda is between 0 and 1/5, then these two terms are both positive. And if these two terms are both positive, to make the max, you want x1 and x2 to be as large as possible. So we want x1, x2 to be both the largest. And so what are the largest values that x1 and x2 could take in this region? They could be set equal to 3, each of them, because like the conditions are that x1 and x2 are less or equal to 3. So you take them x1 and x2 equal to 3. And so in this case, the max, right, would be 20 lambda plus 2 times 3 times 1 minus 2 lambda plus 3 times 1 minus 5 lambda. And that simplifies to 9 minus 7 lambda, if you do it. So that is the value for the max whenever lambda is between 0 and 1/5. So this is the max that I called C lambda. That making sense? So far, so good. Second case, okay, the next case would be, for example, like the next one in between, like obviously like 1/2 and 1/5 are kind of like the magic numbers here, because this is where like the parentheses, like the things in parentheses change sign, to become positive or negative. So when lambda is between 0 and 1/5, both are positive. The other option would be when lambda is between 1/5 and 1/2. Okay. So another case is when lambda is between 1/5 and 1/2, because in that case, 1 minus 5 lambda is still positive. Sorry, that this one is now a negative, and 1 minus 2 lambda is continues to be positive. So this is a case where they have different signs. One is positive and the other is negative. Okay. So let me copy paste the function here. So what I'm saying is that, oops, sorry about that. I used the wrong function. Copy paste. So what I'm saying is that this quantity would be positive and this quantity would be negative. Okay. So it's again the same idea. If you're trying to find the max, you're trying to find a max. So you don't want the negative stuff to contribute at all. So you turn it off by setting x2 equal to 0. That way this doesn't contribute anything negative, because every time you have something negative, you drop the value, right? So I'll turn x2 to 0 and then x1, because it's next to something positive. I do want this one to be as large as possible, so I'll continue making it 3. So what I'll do here is take x1 to be 3 and x2 to be 0. Is that making sense, the logic behind it? And so the max in this case would be for these values of lambda. All right, why did I put L for L for Lagrange, but it should have been lambda. What was the notation I was doing? Let's just go to the previous notation. Would be 20 lambda plus 3. Okay, 2 times 3 times 1 minus 2 lambda plus x2, which is 0 now, 1 minus 5 lambda. And that gives you 6 plus 8 lambda. Whenever lambda is between 1/5 and 1/2. that okay? Is that making sense? And last but not least, the last case is where lambda is greater or equal to 1/2, because in that case, all the terms in parentheses are zero, are negative. So the last case is like what happens if lambda is greater or equal to 1/2, because in that case, 1 minus 5 lambda is negative and or non-positive, and 1 minus 2 lambda is negative. So this one is negative. This one is negative, this one is negative. So if you were asking for a max, you want no contributions for these from these two. So you have to set x1 and x2 both to 0. So you take x1 and x2 equal to 0. And in this case, it's okay. Like it's easy to see that the only thing that survives is a constant term 20 lambda. So in this situation, the max would just be 20 lambda for lambda uh, greater or equal to 1/2. That making sense? That's about that so far so good. Okay, so again, for any possible value of lambda, those are again, like the way to interpret this is like if you choose a value for lambda between 1/2 and 1/5 and 1/2, that is a value that the max could take. This is a value that the max would take for a lambda greater than 0.5, and this is the value that the max would take for a lambda less than 0.2. Uh, what I was saying is that you kind of like this depends on lambda, and it's like a piecewise defined function. So you can look at the graph of this function with respect to lambda. So the first line, this is like a decreasing line, right? Negative slope. So intercept is 9. So it kind of looks like this. Then the other one is positive slope, right? It's positive slope. They kind of connect at there it is a continuous function because they're less or equal to, so they do agree, they do agree at the switch. And then the other one is also positive slope, but larger slope, so it's kind of more vertical. And by the way, this is kind of true in general. Like if even if you had if you had incorporated more inequalities into the function, then if you had incorporated lambda one, two inequalities, then you can have like a lambda one and a lambda two, right? And in terms of like lambda one and lambda two, it's kind of like piecewise linear in the sense like the graph would look like planes connecting at the break-ins. But now the break-ins happen at lines instead of points. It's like kind of like this is what I mean. It's as a very specific case of what's called like, I mean, it's kind of like a concave up function, or in a sense, but but the important thing is like kind of like it's always like piecewise linear in some way. And then the mean, like again, the mean is kind of like the closest bound, the best possible bound in this case, because it's like the closest bound to the actual problem. So you can kind of like see from this graph that the mean should happen here, because like after that it kind of decreases, increases. So this is like the global mean, right? So it's actually like a global mean. Uh, so 1/5 was the magical number. So the mean of all over lambda of all these values happens at 1/5, which if you go back to the formula for 1/5, well, you can use either version, but it's 9 minus 7 over 5, which is 7.6. And this occurs at which values for x1 and x2. This happened when x1 was 3 and x2 it was 0, and it occurs. I guess it doesn't matter. Let's see the point. For the first case, I had taken. I mean, like in this case, like right, like it's consistent. So like there are two choices. Like you could have taken 3 and 0 because that matches here, or you could have taken 3 and 3 because it matches on this end. So like the max would have occurred at 2 different points. Like I mean, there's no rule against that happening. Like like or also at 3 because like for this particular function, like that just like at those 2 points, it just happens to match. Uh, the important thing is like the bound itself. So what that's saying is like in the original maximization problem, you cannot go past 7.6. Whatever the answer it was. I don't remember if I have it here. Let me see. I think the bound for the original problem was 7. Like if you actually were to do it like not dropping any constraints, you should find 7. Yeah, if you don't remark, right? If you work with the original problem, the max is 7 and happens at 3, 1. So the point like of doing it this way is that you kind of always get like an upper bound on the max, which sometimes is good enough. Like uh but it's kind of like it's kind of like an interesting approach if you think about it. Like it's very different in nature from the branch and bound perspective where like you just divide the region. Here it's more like you reabsorb some of like the dangerous inequalities into the function. Um, and then you work with an easier problem. Yeah.
How do you get 3-1? It's not just through experimentation.
Oh yeah, like in this case, like let's see, if you literally, I would have like I think I drew it on GeoGebra. I put all the points on the grid and just check which one had like integer coordinates, and that happened to be the largest one. Yeah, but it would have been like by that's the thing, right? Like it would have been by trial and error, like essentially, because even this branch and bound, um, I believe I have to double check this. I'll kind of verify it next time. I do believe that the bound that you get from this method is better than the bound that you get from branch and bound, but I have to double check that. So don't take me on my word there, but I'll verify that.
And also, you just round down what you get for the minimization of C lambda, right?
Because
Yeah.
like
7, 6, 7.
oh no, like you just keep it as it is, like that's fine, like that because the only thing is like it had to be, you know, because like maybe the max would have been 6, right? So it's kind of like weird to say that you rounded out 7.6 to 6, you know what I mean? Like this max is whatever it is. Like the important thing is that, like kind of like the philosophy is like for any lambda that you chose, you get something that's higher than the max. But that's for any lambda. So you try to choose the lambda that gives you the closest one to the original max, and that's why you minimize over the lambdas. But yeah, whether the number itself is the value of the function doesn't matter whether it's like an integer or not. It's more like the points themselves, like the coordinates of the points had to be integers. But we don't particularly mind whether the value of the function itself is fractional or not. That's okay. Because it's the same with like cost, most things like have cents when you buy them because of the taxes. So it wouldn't matter if like the total profit or total cost is like, $100 with 25 cents. Like who cares about that? What does matter is like the optimization problem cannot tell you, let's build 2.5 boxes. So like the excess are the ones who do make sense to ask to be integers, but who care like the value of the max, it doesn't matter whether it was like integer or not, if that makes sense.
If there's some condition that this method work really bad.
I have to okay, the thing is like it is a little bit more ambiguous than that because it does depend on how you choose which inequality to reabsorb into the function. So kind of, I think the way it's used in practice, and that's why I wanted to do this network flow application, because in practice, when you write down all the inequalities constraints in particular applications, it's very easy to see which one is the hardest inequality, and you just put it back into the function. But it wouldn't, I don't think there's like a general theory. I mean, you do have to make assumptions of how you're splitting the inequalities, because otherwise there won't be anything you can really say, you know? But of course, like you don't do it in problems where I'm sure like there are problems where like this relaxation would not work really well, would not work well. But like, you know, those are not the applications that you would mention like as an use of this like, you know, problem, you know what I mean? But yeah, but like definitely there would be I know there's going to be um
Or like if we make it continuous, not integers.
oh, I mean that's totally
Reached bound in this problem.
so if you kind of right, if you okay, there's also a relation there that I have to double think about. Right, if you forget about the integer constraint, this one still bounds the original linear optimization problem for sure. Yeah, like that's fine. Like because that doesn't depend on the values being integer. It's that right now at this part of the course we're just trying to find always integer solutions. But yeah, like you could have done it like forgetting about integer constraints, and with this adding the splitting of the inequalities, you get like an upper bound, you know, to the
We
original.
have reached that.
Well, no, there would still be a gap in general. Yeah. There's, but they're like right, but there are theorems of when it closes. You know, where there is like an actual like tight. You know, where there's no gap. But yeah, there do you do need some requirements. Yeah. Actually, okay, cool. So I do think I have enough time to introduce this application, which is really fun, which is network flow. Where, let me see where I wrote it. Let me see. Give me a second, just because I think I have to find it on my computer. Don't want to spoil the surprise. So let's see. Where do I? Or did I only? Oh, I may have only written it on the. Yes, I'll write it on the board and then I'll kind of copy it here on the notepad. Let's see. Station, let me just remind me myself if I do any of this correct. Yeah, I put them all like on the. Okay, let's see if I think I think that's going to be fine. So let's go back. So there are like these fun problems of like which are called shortest network flows. So this is like an application of this like Lagrange relaxation application of this technique. I may need to finish this problem next time, but like at least I can show you the idea behind it. So again, like this, like a lot of like these problems have applications involving graphs. So imagine that you have a graph. I'll show you what I need in a moment. So let's say you have a graph. So it has 6 vertices or nodes. Those are the usual words for them. So the way in which you think about this problem, this is called like shortest track or like also network flow. I think that's like the usual terminology for it. Okay. The way you think about this problem is that maybe one of the nodes represents the source. So maybe you have like a company, like, you know, you know, like your Amazon, and this is where like all the trucks that carry the packages are located, right? And then you have to you need the trucks to deliver packages through different cities, right? Until they go back to a different warehouse. Like, you know, so maybe it goes from one warehouse to the next, but in between it has to do some stops, deliveries, whatever. So the way I'm thinking about the network is that there's a source where everything comes out of, like, you know, which is kind of like the supermarket or like the warehouse, whatever you want to think about it. So let's call this S for source. And then there's a target, you know, which is kind of like it's good that so many words like NDT, like terminal, target, like, you know, think about this as the stopping point. Okay. And then like the other places in between are kind of like, you know, where you're supposed to you maybe like make stops or things like that. So you could have something like this. Let me just put something like not too crazy. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's leave it like that. So the way I'm thinking about it is like, you know, if you have a truck, for example, if you're a truck here, you could either go up or down, right? If say, for example, if you went up, then you can move to this node, or you can go down to this node first, right? Once you're here, you can go, once you're at this node, you could go this way or this way and so on, right? So the arrows do indicate kind of like the direction of the flow. That's, you know, so it does matter like here, like the orientation of the network in a sense. And kind of like the idea is that okay, so imagine that to each edge, I will attach a cost. So that could be like the amount of money that it takes the truck to go through that particular route. So how many edges do we have? We have 1, 2, 3, 4, 5, 6, 7, right? So we have 7, okay, no, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. I think so let me label them. Okay. Well, I guess doesn't matter in which order you do them. So C1, C2, C3, C4, C5, C6, C7, C8. So each CI is kind of like the cost associated to that edge. So, you know, if you thought about it as a kind of like electrical circuit, like then that could be resistance, like, you know, like because like that's related to the cost for like electricity flowing through a particular circuit, right, or something like that. Um, So far, so good. And uh, then you also are going, like this is kind of what makes this problem a little bit more interesting. You're also going to think that each edge, in addition to having like a cost, has a time associated to it. So it would be kind of like the time that it takes you to travel from one node to the next. So I'll call them T1s. I mean T's for time. So it would be T1, T2, T3, T4, T5, T6, T7, T8. Okay. So for example, if you thought about it in delivery, you know, prime delivery, I suppose usually it's under 2 days. So like you may want to travel along this network in less than 48 hours, say something silly. Or like there might be a constraint, like, you know, again, they were like like you have to go from the source to the target in under 2 hours, you know? So kind of like the problem that we want to deal with is like, I'm trying to choose like a path, you know, I want to choose a path from source to target that minimizes the cost and also is within a certain amount of time. I cannot exceed a certain amount of time to get to the target. So this is going to be different. Like there's another famous problem, which is called the traveling salesman problem, which some of you might have heard, which is like if you have a bunch of cities, what is the most efficient way to travel through all the cities? This is a bit different because I'm not asking you to go through all the possible edges. I'm just trying to find like kind of like a way to go from source to target in the least minimizing cost, but also within the time constraints. So kind of here, my problem is that is like, for example, the path could go like go up, then down, then up, then down again. That could be the path that works. But you see, I'm omitting certain locations there. Like, I'm omitting like that. Oh, actually, I would have just dropped that last edge that you see there. But like maybe the optimal path, depending on the cost, could have been just to do something simple like this. Okay, so I'm not requiring to visit every location. If you do that, that's a traveling salesman problem, which is like a very famous one. So the goal is to minimize the cost, but also completing okay, let me put it better. You're searching for a path from source to target, searching from S to T that minimizes the cost of the path, but also is completed, the path is completed in under a certain amount, which I'm just going to call uppercase T. But the travel is completed under a certain amount of time. But okay, so far so good, everyone with me? The problem making sense? So, okay, so again, I'll maybe start it today and then tell you on Wednesday how to set it up, but it's really fun. Like, I mean, this problem is, again, kind of like the interesting part of many of these problems is just how do you find the right variables to set everything up so that it works? Because once you have the right variables, everything is like applied simplex method, or like I'll tell you why this lagrangean relaxation works nicely. But kind of like the idea, kind of like before, is like for similar to what we did with the graph from the movies and the people, you will introduce a binary variable for each edge, where like the meaning of this variable will be that it is one if the edge happens to be part of the path, and it's zero otherwise. So in this case, there 8 edges. So you introduce binary variables, x1 up to x8. Again, a binary variable is just a way of saying that it's a variable which is either 1 or 0, true or false. That's how you should always think about them. So each xi is either 0 or 1, okay? And 0 means that it won't be part of the path, and 1 means that the variable would be part of the path, optimal path. So xi is 1 if the variable, if the edge, if the edge is part of the path. Okay. And then, so what you would like in this problem is that what you're trying to minimize, you're trying to minimize the cost, right? So you like, it's kind of similar to what we had done before. So what is the function? In this case, the function, or like you're minimizing, is that you're trying to find the mean. Okay. So like, there are 8 edges, so you want to minimize the cost, but this is the wrong function, right? Because this is almost pretending that all the edges were being included, right? Not necessarily all the edges are included, but the way to fix that is just multiply each cost by the xi variable. Because that, that only gets activated if the, if the variable if the edge happened to be part of the optimal solution. So that is like the cost, the way you want to understand it. So that's the function. In this case, it's more naturally like a minimum. You could also have set it as a max if you wanted. If you think about it, how much the truck driver is getting paid, I don't know, for, like driving through like a particular route. So like, like then they would maybe want to maximize their profit. But it usually is more like natural, this process as a mean. Okay. And then, okay, so this is a function. Each of the it's a you have to imagine that the cost and the times are kind of given. So like the function depends on x1 up to x8, right? So those are like the variables in this problem. They're binary. Then one constraint is the time constraint. Okay. Which is, again, that the times cannot exceed a certain amount of time that I gave you. So, the T1 plus T2 ... plus T8 cannot be exceeding this amount of time that I gave you before. But again, this is similar to what we discussed. Like if you just do it like this, you're pretending that all the edges were considered in the final solution, but they're multiplied by their corresponding binary variables, because that way you're only adding the times along which you actually drove, So you get T1 x1 which more elegantly you can just write as this is that making sense? So far so good, everyone with me? Okay, and then I guess I don't have time to finish it up, but I'll write the next one, like the extra conditions next time, but at least I'll explain what's left. So this is not the end of the problem. There are more constraints hidden, which kind of makes sense if you think about it, like from like a flow perspective of driving. Because imagine that like first, like something has to come out, something has to come out of the source, right? So you had to either like choose like up or down at the source, right? So the way to say that is that x1 plus x2 should be 1, because that means that at least one of them, these two had to be activated, right? And then, for example, so it's kind of like a conservation of mass. So if you imagine like a fluid kind of emanating from the source, it can only go up or down. So like like you have to impose that as a constraint. And then, for example, if you went here, right, you have to say that the incoming fluid, has to split like in one of the possible paths. So like if you got here, like you either have to go down or right. So the way to write that as a kind of like a conservation law is that x1 would be what, x2 plus x7, because what comes from the left, had to either go right or down. So kind of like at each vertex, at each node, you have to look at the conservation law to say that you have to navigate the flow, right? So you have to impose, you get like an equation per vertex, per node. And so there would be, how many nodes are there? 6. So there's 6 extra constraints, right? Which I'll write next time because I don't have time now. Which are conservation laws, if in a sense, like conservation of mass, if you think about it as a fluid, conservation of mass. But kind of like if you, not that we're going to solve them, we're just interested in setting it up. But kind of like this usually is attack using lagrangean relaxation, and this is kind of like the constraint that's incorporated into lagrangean, that which kind of makes sense, like because because it involves like in a sense like all the variables, where the others are more like specific to the particular vertex in question. So it's kind of like useful to know that these things, that's how it's used in practice. Okay, so next time I'll finish this example, write it in down, And then I'll tell you the last topic, which was like this disjunctive programming. How do you find max on non-convex sets, which are unions of convex sets, which is also a fun topic. So we'll talk about that on Wednesday. And again, I'll give you your exam grades by the end of the week. I just was finishing writing the problems, for the practice. Over the
Look at
weekend.
an example, practice problem for like example, test. Or
Not particularly a test, but it will be kind of like, I mean, there will be a problem from each of the new topics, right? And then like, I'll probably take a problem or two similar from each exam, like, so it's kind of like, I just haven't decided the number of problems, but if it's like, no, I mean, they're shorter because they will be mostly setup. I think I had said in class that I wouldn't I will ask the simplex method once, but just to solve it.
Okay.
Everything else will be kind of mostly setting it up or like doing graphical solution.
so it will be like a 3-hour exam. or
It is
just-
more like I mean, like, well, many people have finished the exams even like half the time, but no, I more like 2-hour exam,
or
like,
it's supposed to be a trip.
it's just like a little bit longer. I think I have been using 6 problems for these exams, right? So probably I'll go like with 8 or 9, but but like only one where it's actually computing things like in the with the simplex method, because like that just takes forever. Like I just want like to remind you, okay, you know how to use the simplex method, and I'm happy with that. Like, and then the others would be like,
And-
if you had to perturb, for example, if you had to perturb it, write like, how you look with the perturbation. So many will be right. So like, they, that's why I just have to decide how to break it down. But at least obviously there will be one for each of the new things, But again, like this would be kind of like write it. Like, so I give you a network flow, you set up the problem because I don't want you to solve it because like it's a waste of time. Like, like no one really solves this in practice.
Yeah,
Like,
we-
like you put it on a computer. So what's the point of like doing it like in a way that you would never use it? Like, you know what I mean? But you do need to know how to set it up because that's the only input where humans are still needed. But like, yeah. But at least there will be one problem with the simplex method of like actually solving it. Everything else will be mostly set it up, or like in those which I have been given where are 2-dimensional, so you can do the picture, kind of like the branch and bound, because realistically I could not ask anything besides like something that can be done on the plane, where you branch, but like it would be fast because then you just see from the picture, okay, this is how you cut it, like the region. So if it's not graphical, then it would just be like writing it up basically. Yeah.
Yeah, thank you.
Okay, sure.
So does the